In this video, I'll go over the mathematical models that are associated with phases and phase changes. So, first is the ideal gas law. You have probably seen this version before in chemistry. PV equals nRT. So this is the pressure of the gas, the volume of the gas, N is the number of moles, where 1 mole is 6.02 times 10 to the 23rd molecules. R is the ideal gas constant, and T is the temperature. This temperature has to be in Kelvin. This can't be in degrees Celsius. It can't be in Fahrenheit. It's got to be in Kelvin. And the reason for that, if you think about outside, actually the temperature right now is very close to freezing. And the temperature in Celsius at freezing is 0. So if the temperature is 0, that means either the pressure or the volume has to be 0. And when the temperature reaches 0 degrees Celsius, neither of those things happen. The pressure doesn't immediately drop to 0, and all of the molecules in the air don't immediately collapse into 0 volume. So this has to be in Kelvin. Okay, so that's the ideal gas law that you probably know from chemistry. The one that's usually used in physics is this one. P is pressure, just like down here. V is volume. T is temperature. So those three things don't change. They're the exact same between these two equations. The two things that are different, lowercase n versus uppercase n. This uppercase n is the number of molecules, not the number of moles, number of molecules. And Kb, this is Boltzmann's constant. So Boltzmann's constant, you can figure out what it is just because little n times r has to be equal to big N times Kb. I put a b down here to remind me that it's Boltzmann's constant. We've already used K for the spring constant, and there are actually several other lowercase k's that you'll run into in physics. So to me it's important to put the b there so I don't forget which K I'm talking about. In the textbook, this b is not there. It's just called nkt. Now for the internal energy of a gas, we said it's related to temperature. You can see that the internal energy is actually directly proportional to temperature, in Kelvin again. NKBT, that looks very similar to what this is. So 3/2 NKBT is just the internal energy of the gas. And finally, we have the latent heats of fusion and vaporization. So Q here, this is a heat, is mass of whatever you're talking about, times LF. This L, that's the latent heat of, the F means fusion. So fusion, that's the transition between liquid and solid, or solid and liquid. The one down here, the V, this looks exactly the same except for the V. The V is vaporization, and so the vaporization, this is valid when you're going from liquid to gas or gas to liquid. So this Q is the amount of heat that's required to melt, solid-liquid transition, a certain mass of material. This L will depend on the material itself. And this one tells you how much heat is required to boil a certain mass of some material. So these L's you'll have to look up in a table. There are tables in the textbook for that. And this is also, if I have a certain gas, this tells you how much heat has to be removed from the gas to get it to change into a liquid. And similarly, if I have a liquid that I want to change to a solid, this tells you how much heat you have to remove from that liquid to get it to change.